No. Yeah. Yep. Yeah, I like the design was military. Yeah, that was good. Well. Okay. Oh. Who got the Warren? They. That's the living room on.
Hello. How does it?
Okay. We were rehearsing yesterday for my play,
Oh, yeah, how'd it go?
and so I was being like funny, so I was like my elbow on someone's shoulder,
Uh-huh,
and he was on a roller chair because he pretended to be tied up for
yeah,
to play,
yeah.
and he moved the chair, and it was this elbow, and I hit my elbow.
Oh,
Yeah.
did you get your funny bone? That's the worst when you do that.
Danny, for some reason, Emma always goes out.
What does?
Emma always goes
Oh, yeah,
out.
she does, she's busy. She's a busy person, I'm telling you. It's amazing.
You probably see how many homeschool events that my mom has lined up.
Oh, yeah, she keeps you guys busy.
Mom. Emma's mom was like the head of the.
Yep.
My mom's in that.
Oh, yeah, that's great.
My grandparents live in Pennsylvania.
Yeah.
Well, my dad's parents live in India.
Yep.
Okay. I'm trying to get another color started. Can you start with yourself? Look. For me, it's super easy. Yeah, that's why I'm trying this one. Miss Danny said that one has been on like the table of like at her
Yeah,
grandparents'
one just like that. Yeah, I don't know what happened to theirs, but it was one exactly like it, so years later, I bought myself one
So
just.
now I take the challenge of.
You do it. You do it. Seems like everybody works on it a little bit every week, or a lot of people do every week. A little more is added, a little more here, a little more there.
But then it's also annoying because it feels like your progress get mixed
That
up.
bottom one is actually that puzzle stuff. I got two colors, but I just got mixed them up. When I was trying to solve the third one.
No,
Oh, you got two done on this one? Oh. So it did.
Miss Danny, can the colors of this puzzle be anywhere?
puzzle. Oh, I think so. I mean,
That should be enough.
okay. Finally. Thing I ordered for my mother for Christmas is finally gonna arrive today. It's been super late.
This one was really hard. The pink part is easy to do. Maybe I'll just try to do it again, but I don't think I'll be able to solve more than one side.
I got two sides when I was solving the third one. It got me.
On this thing, the talon. How did you get the ball, all the color balls to all be on?
I know. That's the.
Maybe if I just start like getting the color.
I don't we got this. And we need to put that there's some. Yeah. This side. Yes.
It's that automatic. If not, it means B.
No, wait a second. What if we just do the top? Okay, that. Yes.
Alright, I can't figure out how to do more than. You know, I'm just like. Does Danny, do you
Yeah.
have any more puzzles?
Yeah, I do. I'll have to bring some down. I have lots of puzzles. I have some upstairs. I very much enjoy puzzles. No, most are upstairs. I do have, so there's, yeah, there's that one, and then in here are actually two. One is a pyramid and one is like a cube. Oh, this one's together. I love. There's one that's like a ball, and it's these pieces like this. And it makes like a weird ball. And then there's a pyramid and a cube, and they're all kind of mixed up, and somebody put a random duck in there. I don't know. And I don't. I just not cute. It's just a ball. It's like a weird kind of ball. I don't know. There's all kinds of random pieces. I'll have to spend some time making sure they all come together now. Yeah, they're the ones that actually kind of put them back together once they're disassembled. Others upstairs. I like stuff like that. My dad used to carry little things around in his pockets that were little puzzles. He made one that was like a little metal tube, and it had a loop of twine on the end of it. And he would tie it around people's buttons on their shirts, and then tell them to get it off. And it was real. Nobody could ever figure out how to do it. It was really. He thought it was hilarious because he had people walking out with a little tube hanging off their shirt for hours till they either gave up or figured it out. Most people just gave up and said, all right, fix it.
Well, a little prankster.
Oh, yeah, he is. He's still a prankster. Actually, last year for his birthday, I bought him this year. Actually, I bought him a bunch of little practical gifts. Practical jokes, sorry. Gifts that were practical jokes that he could do to the people that come to his room, like the nurses and stuff that visit him. So he could play jokes on them all. Because that sounds like something he'd enjoy.
Gifts that are the best gift, or also the worst gift.
Worst if you're on the receiving end.
daylight savings.
Yeah, did it mess you up? Yeah, it always messes people up.
Had to wake up 7 o'clock for class.
Yeah,
And then after that, like now I have to wake up at 6 o'clock.
yes.
To India for a Hindi or class.
Oh, you're doing Hindi class? Yeah.
And that and I have to wake up at 7 o'clock to do that. Now I have to wake up at 6 o'clock. And the teacher's like, tell your son to wake up at 5:45. Like, what?
Oh my goodness, you're not awake enough, huh? Oh my goodness. Wow. Yeah, yeah, those are, I agree, they're hard. So how much Hindi can you speak already?
What?
How much Hindi can you speak already? A little bit. I know one word. That's as far as I get with Hindi. Just one.
What?
Sure.
Oh, shut up.
Yeah, very good. That's the only one I know. Yep.
That's ironic.
One of my husband's best friends from college was a bridesmaid in our wedding. And she's Bengali, so she taught me a couple things. Chup was one of them. So she'd look at us all the time. We'd be rambling on. She, chup. I'm like, okay, Remy, sorry. Where's the rest of your crew? It's 10. Some slow people. I'll give them like 2 minutes. Maybe they're stuck. Yeah, I was gonna say it's unpredictable these days. You just never know.
Like me and my grandma are usually like, they were like 20 minutes early. I always be like respectful and only come in like 10 minutes.
Yeah.
Junior lab rats.
Maybe it is. Maybe I clicked the wrong one up. Good call. I just saw it. Let me see. Let me see if that's actually right. I have them both. I just may have opened the wrong one down here. Oh no, I just didn't put junior in when I forget that. Sometimes when I'm putting them, I'm making the slides because I do yours second, theirs first. So, oh, hello, here they come.
Darcy, I'm guessing, you were in junior high when you went to Army, when you went to Army, right?
Yes.
Okay.
Good crew.
Oh, geez, I'm thinking. You know exactly right?
One like that was there.
Oh, yeah. Yesterday, we were doing the play, and he was like the main character, and we had him tied up. And I was being funny while he was tied up, and I put my elbow on his shoulder to be, like funny. And when he moved the chair, because of the spinny chair he was sitting on, my elbow did not. An object at rest stayed at rest. It went down and then out.
Y'all are funny.
But
All right. Well, good morning, people. How are we? Everybody awake after our time change?
no.
Woo-hoo.
Sleepover, as the time change is happening.
This is the easier one in the morning, but the harder at night. Like I'm tired about 9:30 p.m. now. I'm like, okay,
I'm tired at 8:30.
look, it's dark so early. It's
I'm like, did it get dark? My soccer practice is like at, I think it's by 5:30 and it's like getting dark at this time.
yeah.
Like, but then it's freezing for my 7. They like freezing seems counterintuitive.
I agree. It's all silly.
It doesn't even matter because they just switch around the times a bit, like the days stay the same.
Exactly. They should just leave it the same.
I
But
know, that's what I was
a lot of
saying,
places
I'm
are
like,
ditching it. A lot of states are ditching it.
just needed it for something.
Yeah, back in the day, but
It's not back in the day anymore.
we don't need it now. Move on. Well, all right. We are starting a new unit and a new quarter. Dun, 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 dun. Also good. I think everybody here had their unit 3 tests turned in
What
yesterday.
did you get first quarter A plus or?
I honestly
I'm
didn't
sure
check.
A or A.
Well, that's what I'm about to say. So what I'm gonna do is I'm gonna be issuing your progress reports over the next 2 days. So I had to wait for everybody to finish their exams before I did that. So last night I got all of yours and then I got 2 more of the senior group just this morning. So
I got 3
Over the next
questions
2 days.
wrong on my exam.
well, we're gonna go over some
I
questions.
put 7 steps
Mm.
instead of 7.
Okay, so first off, good point, Darcy. All right, so if you have like a fill in the blank, okay, on an exam, And for example, there was one of them where it talked, the first question, I think it was, talked about what was your average speed or whatever.
Yeah.
And I put blank MPH.
Yeah.
If in the blank, 8 was the correct answer, but if in the blank you put 8 MPH or 8 miles per hour, the auto grade computer system is gonna count it wrong.
That's what I got.
But I go back and fix it. So when I grade your tests, I go over everything that you missed and I look at every question you missed to figure out, did you just not know it, or did you maybe spell wrong or something like that?
I did 7 steps right instead of 7 steps
Yeah.
left. Yeah, I was
Mhm.
about to, I was like, what is my brain doing?
Yeah. And I will always give you partial credit if you give me part of an answer. Like there were some where it's like, here's your Newton's first law, state it and give an example. Well, if you stated it, but you didn't give an example, that's like about half credit, right? So
Oh, yeah.
always do your best.
I always do.
I got half
Yeah.
credit on, I think, number 2, but number 1, I gave a very good example.
All right, so let's have a look here. All right, so first off, I do want to go over these because these are important. So when I say take note, I mean like literally take note. You might want to write a note or two. If you look at these and you go, oh, I got that wrong, you might want to think to yourself, okay, I'm gonna take note of this because these could show up on your midterm and you don't want to be getting them wrong a second time, right? So Carlos, Louis, are you guys, is the sun too bright? I can pull that blinds down. Yeah, let me do that. You're blinded. Carlos's back of his head's getting toasted and Louis is blinded. I gotta stand on my
Not anymore.
I'm stepping on my own
There you
clothes.
go.
Classmate.
Yeah.
I'm talking so heavy that I have to lift it.
I'm so
You should go to your
Right?
Sorry.
Okay.
Be a goat. My thing is just a mesh sheet, and when the light hits it, I cannot see the dark. So annoying. Lot very bird.
Is that a scrim? You got a scrim to deal with? All right, so your most missed questions. All right, the first question that I have here is this one. All right, and 50% of you got it right. So the question says, read carefully, and this was a true or false. Change in position equals initial position minus final position.
Oh, yeah.
Tell me what's up here. What's up with this, Eunice?
It's final position minus stage.
Yes, okay. That's what we need. Read really carefully. If I go from here to Taco Bell and I want to know how far I went, I have to take that Taco Bell and then subtract from here. That's how I find out, right? Yes.
Why are you going to Taco Bell?
I love Taco Bell, man. Taco Bell is life. Get you a Nacho Bel Grande or one of those Doritos Locos. Those are good.
Talk about the back.
Dude, but it's so delicious.
I just hate like chicken.
So the next one was this one. Acceleration is given in meters per second. And yes, 50% of you missed this one. Yep. It's meters per second, or meters per second squared. Right. So
I don't remember.
what's given in meters per second?
Velocity.
Speed.
Acceleration?
Yeah, speed. Uh-huh. So there you go. All right. The next one was this one. Compare and contrast
I think I
weight
did a
and
good
mass.
job.
You think you did a good job with this? Well, okay, 67% of you got it right. Still less than 70. If it's less than 70, I'm going over it. That's how it works. All right. So compare and contrast. You got to compare. So the easier one here is the contrast, right? Okay. Somebody tell me what's the difference between mass and weight. All right, Emma, what's different?
Weight can change like in space.
Yeah, why does weight change though? That's the important part.
Because the gravitation.
Wait a minute. Darcy?
I was all like, weight, the size. With mass, I was like the size of something that would determine it. It was something
It's
like
the
the
matter
size
in
of
an
an
object.
Yeah, there you go. All right. So the mass is amount of stuff or the amount of matter in an object. The weight is gravity's effect on that object, which is why it changes, right, Emma? Because if you go to space, you have less effective gravity because you're further from the surface of Earth. So therefore your weight will change, but your mass will not. That's the contrast. What's the compare? Well, they're both measures that are important when you're dealing with forces. They both are given in the same units. We use gram, right? So these are all possible compares. And you could also say they both depend on matter. That's another compare. Yes, Miss
So if
Darcy.
you're going like more toward the surface of the earth, say in like maybe 50 years, humans go like pretty close to the surface of the earth.
Uh-huh. Well, we're on
Would
it.
you
I'm
get
pretty close to it right now.
Can you get like a lot heavier?
You mean the core? Yeah, I mean, yeah, technically. Mm-hmm.
That
So for an example, you could say they both depend on matter. Mass is how much matter an object contains, whereas weight is the effect of gravity on that mass. All right. Next one was this one. In your own words, describe Newton's second law and give an example of how this law may be observed in everyday life. Now, this is the hardest of the three, right? The other two are catchy to remember. Again, this was 67% of you correct. Okay, who can put, what's the easy way to remember Newton's second law? Do you remember?
Equals MA.
F equals ma. And if you remember that force equals mass times acceleration, then you can say that force is proportional to mass, because if F equals ma, then whatever you're multiplying m by, F, because it's the product of that equation, is also going to get multiplied by that same amount. So F and A are proportional and F and M are proportional. So an example of it is also a tricky one. So F equals ma. So you could say moving a heavier vehicle requires, let's just say requires, I read it last night, more force than moving a lighter vehicle.
Equal MA.
Mhm.
I was like, oh, maybe I shouldn't, but that's the best way to describe it.
Yeah.
I feel like when we kick a soccer ball, the
Mhm.
the force, like what did I put? Yeah,
Yeah, well, however much force you alter the amount of force.
I
Right.
the race car example that we did on Get Tricky with You.
Yes.
Where if
The
you put
cars.
more, if you put two cars and you use more force.
Mhm.
on one.
So if y'all remember when we did lab, what was that? Was it
Tricky
10?
with-
Was it lab 10 where we did the, getting tricky with Newton's laws lab? And I said, you're gonna want to keep this lab and you're gonna want to study this lab because you might be asked to give an example. So that is a perfect thing to study. So if you're going, okay, I know she's gonna ask me, and I'm telling you on your midterm, I know she's gonna ask me to state each of Newton's three laws of motion in my own words and give an example of each. So that you're not sitting there during the exam trying to come up with an example. Go look at that lab and pick the one that's easiest for you to remember. The two cars, the checkered flag. That's the perfect F equals ma, right? You had the two cars, you had to push them, then you had to push them and push one a little harder than the other,
Mike
right?
got that right because recently I had watched some show called Grand Tour. They do like drag races all the time. And one of the cars won. They had the same speed, but it was a bit lighter.
Oh, yeah.
That's what I was thinking.
There you go. So yeah, so what you want to do is you want to say like, and the checkered flag lab, but then you want to explain too. In order to get one car to move faster than the other, I had to push it harder, right? So you have to explain what it is. So just state, like some people said, riding a bike. What about riding a bike? There's a lot of things you do when you ride a bike. You balance, you steer, you pedal. Yeah, there's a lot going on. Okay, how about this one? Newton's universal law of what? States an object in the universe attracts to every other object. 50% of you got it right. Okay, Carlos, what you think?
it's not forces.
Nope, it's not forces.
I put gravity. but
It's gravitation. Yeah, and if you put gravity, I corrected it.
Oh,
Because you were
you
close. If you put gravitation, you got it right. If you put gravity, then it was one that I auto graded and
Yeah.
went back and was, manually graded. It's like, okay, close enough. We know what we're getting at. But yeah, we're talking about, it talks about every object being attracted to every other object. So it's not forces, it's about gravity, right?
It's force, and then I went back on it. I'm like, no.
So what's this one? The result of a force distributed over an area. Oh, 33% of you got it right.
I put
Verse,
four. I put.
take a force, put it over an area. What am I doing? Pressure. I'm pressing.
I put pressure.
There you go. If you put pressure, then you're one of the 33%.
I think I put pressure, but I
Mm.
but I-
So force over area is pressure. Okay.
Friction on one that the answer was that, not
Same.
friction.
All right. This one got a lot of people, 17%, which essentially for this class means one person got it right. The SI unit for pressure is not the Newton.
Pascal.
It's a Pascal. The SI unit for force is a Newton.
Oh, yeah.
Pressure Pascal, PP, remember that?
I
And
forgot.
Newton has his laws of motion and forces and all that business. Newton's your force, Pascal's your pressure
I
guy.
don't even know what I answered.
Remember our little Pascal rat? We took like this whole little journey on him. Like where was he born? He invented weird things, bus lines. Remember all that? Yeah. So spray bottles and atomizers function by taking advantage of what principle? 33. Bernoulli is right. Yeah.
I didn't get that right.
Yeah, this is where y'all put in Pascal. Remember, Bernoulli's the one. Do you remember when we took the big bag and we blew into the bag? Do you remember that?
Yeah.
And it blew up really fast and we blew from behind as opposed to this.
Wait,
Right.
what was that? I don't remember half of it.
You might have missed that. That may have been when you were absent.
Oh, that might have been.
So then water pressure does what as depth increases?
Oh, I
Yeah, and then air pressure decreases, right? Because you think you swim to a bottom of a pool, your ears are like, ow, they hurt. I don't remember who it was what. This question was on both sets of exams, so I had 22 people answer it. I don't remember who got what. All right, so let's move on to our new quarter, new unit. Now we're like for real into the physics stuff. What is work? Okay, work is everyone's favorite thing.
No.
Doing work requires, Darcy,
exerts force and distance. Force and distance.
force on an object to move it some
Moving car 5
distance.
minutes away.
Did you? Okay. So doing work requires exerting force on an object to move it some distance. If I just press on my desk and I'm pushing and it's not moving, am I doing any work?
No.
But if I press a little harder, am I doing work now?
Yeah.
Yeah, because it's moving over some distance. So in order to do work on an object, the object must move some distance as a result of the force. So if I'm pushing on something and nothing's happening, but then a big wind comes and blows it away, I didn't do the work. The wind did the work. Right, exactly. In order to do work on an object, the force you exert must be in the same direction as the object's movement. If there's a box here and I'm pushing on it and Darcy's pushing on it from the other side and Darcy moves it towards me, Darcy did the work because it was in the direction that she was pushing, the direction of her force, not in the direction of my force. So we think about canceling forces. If she's pushing this way with 70 newtons and I'm pushing this way with 50 newtons,
She's winning by.
she's pushing by 20 newtons, right? 20 more newtons of force on her side results in the work because our net is now going to be 20 in her direction, which you would say like is the positive X direction or negative X direction, depending on how you want to do it. So work depends on direction. Any part of a force that does not act in the direction of motion does no work on an object. I could push on that box all day long, and if it doesn't move, I'm not doing any work on the box. Now, am I doing work in another way? If I'm doing work on the box, I mean, I'm not doing work on the box because I'm pushing, but it's not moving. I am. There's actually the muscles in my body are doing work, right? Because they're working against my skeleton, so they're moving. Right, my muscle is pushing an arm down or up or moving it around. So actually within my body, work is being done, but not outside. Yeah.
Technically speaking, you are always working even in your sleep because your heart is moving your heart to make.
On your brain because
Mhm.
if your brain stopped working, you're slow.
That's a different kind of working, but yeah. You know what I think I forgot to do? I was going to get Wilhelm out for today. I have to bring him out. He's he's hanging out in the bathtub right now. Actually, it looks like a dead person. Okay, here are players. All right. We have joules. All right. Here's how we remember this one. Joules here. It takes a lot of hard work for joules to mine these joules. Okay. When we're talking about work and joules, we don't spell it this way. There's an O in it, right? But this is how you can remember that joules are the units for work, right? Because it's a lot of hard work for joules to mine these joules. Now, this dude over here, he is Watson. All right, with 2 T's, right? And I wonder what Watson had to do to become the most powerful rat in the world. So if he's the most powerful rat in the world, then you know that watts measure what? Power. So joules measure work and watts measure power. So if you remember, what did Watson have to do to become the most powerful rat in the world, and that Joules had to do a lot of work to mine the joules. Okay. Now.
Like, you got the easy part.
Yeah, maybe. So in science, you do work on an object when you exert force on an object, which causes the object to move in what? What you got, Eunice?
It causes the object to move in the forward.
You got it.
In the
I've just got to move in what direction compared to the force?
same direction.
Same direction. It's got to go in the same direction. It's not going in the same direction again, not work. So he's pushing the cart, right? And presumably the cart is going to roll forward the way he's pushing it. Presumably. That direction, right? That's what we hope. And it's work. You good over there?
Pushing it.
Nico, Lewis, you good? All right, so see, he's working. Phew, it's work to push this cart. All right, how do we calculate work? All right, so what was the SI unit for work? We just said it. Okay, Nico? Yeah, it's joules. All right, the joule. So 1 unit of what? Moving an object, 1 what? It's also called a Newton meter. It's 1 unit of, Emma?
Force.
Okay, moving an object, 1, Carlos?
Meter.
1 meter or a Newton meter. Now, do you see how that makes sense? Unit, we measure force in newtons, measure distance in meters. So 1 unit of force to move an object 1 meter is a Newton meter. It's also a joule. And if you're using a force to move an object in a direction, you are doing work. Therefore, your unit of work is the joule. See how that makes sense? It all kind of works together, right? Yeah. So we abbreviate it. Yes, Nico?
And
Newton meter, yep, N times M. Very good. All right.
By the way, I love the bottom thing here. It's like hashtag not from Home Depot.
Yeah. Yeah. In a minute, I'm going to go actually grab him. I left him in the shower. I meant to bring him out here. So, Wilhelm, so you can look at his joints. All right. So sometimes the D is shown as an S. This is your distance here. Work, force, distance. Okay. So sometimes you'll say that D shown as an S. So don't worry if you do. All right, so here is James Prescott Joule. Watch a little thing on him and I'll go grab Wilhelm since I forgot him. Okay, you can.
All these things, all these unit of measurements are named after.
Yep.
Today's story is about an English mathematician, physicist, and a brewer. A scientist who linked between the heat concept and the mechanical work and hence the formulation of the first law of thermodynamics. By such discovery, his name was named after the energy measurement unit. In short, he is James Prescott Joule. Bailey Street in Saltburn. James Joule was born in 1918. He is the son of Benjamin Joule and Alice Prescott, where his father was a rich brewer. Joule was affected by the ideas of the chemist William Henry and some engineers from Manchester when he was young. In 1835, Joule studied at the University of Manchester alongside the English chemist John Dalton. Electromagnetic engines and their strengths and drawbacks in comparison to steam engines were among Joule's initial scientific concerns. His involvement with the family brewery helped him to focus his attention on engines that increased productivity. Joule was focusing on the management of his father's brewery, where later he improved his father's business by replacing his engine with a new electric motor that he built. In 1840, Joule published a paper describing the Joule law, stating that the quantity of heat generated per second in a wire carrying a current is proportional to the wire's electrical resistance in the square of the current. As a result of that, the SI unit of work was named after him. In 1843, he did a famous experiment that proved that heat is a type of mechanical energy. In 1845, he delivered his paper on the mechanical equivalent of heat to the British Association in Cambridge. Joule computed the mechanical equivalent of heat as 4.1868 joules per calorie of effort to raise the temperature of 1 gram of water by 1 Kelvin. Joule received honorary degrees from Trinity College Dublin in the year of 1857, the University of Oxford in the year of 1860, and the University of Edinburgh in the year of 1871. In 1878, Joule was awarded a civil list pension of £200 per year for his contributions to science. In the year of 1854, his wife and infant son died. He never married after this traumatic incident. Joule became very ill in his last few years of his life. To keep himself going, he relied on a well-earned salary from the British government. Joule died on October 11, 1889 in Sale and is buried in the Brooklands graveyard with the number 772.55 written on the grave headstone. This number refers to one of his discoveries, which is the climacteric 1878 measurement of the mechanical equivalent of heat. That was a brief biography of the English physicist and mathematician, James Joule. We hope that you enjoyed it. More stories will be coming, so ensure that you're subscribed and click the bell icon.
Very well, I
Please
like
help
this
us by
John.
liking, commenting, and sharing.
I love his.
This encourages us to deliver more. Wait for the next video on the electricity and magnetism channel, and we'll see you in the next one.
Committing crime.
All right, so there you go, direction and magnitude. Oh, moving on, moving on.
The way he's just dancing.
So, work in the body. Now we have our friend Wilhelm back.
Oh my God,
Right.
his sister.
Yeah, there you go, man. Ah. All right, most machines in your body are what? That consist of bone and muscles. Emma. They're joints, but what do joints basically turn out to be if you look at them as machines, Darcy? Levers or levers, yes. Okay. So this is why I don't mind his legs being off at the moment.
I'm sure he doesn't mind either.
So what's this?
It's a leg bone.
What leg bone?
Chin. Chin.
Where in the body? Where's this go? Here? 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 Yeah. Yeah, it's a femur, right? Femur is the thigh bone, goes here, okay? And oddly enough, this skeleton is real close in size to me, so it's kind of thick. Mine's probably right that size. Now, what's this then?
A leg.
Great, so what's this one?
Shin bone.
Shin bone, what's the other word for it? Do you know? Tibia.
I know.
And this is a fibula.
Try not to hit with a razor scooter. That kills.
We want to attach.
This is how God did it, everybody.
Now let's see. There we are. Does this look like a leg to you?
Yeah.
Yeah.
Pretty much how it goes?
It doesn't look like a foot, but
Yeah.
it looks more like a hand than a
So,
foot. Do you think
Says it's a lever, right?
Yeah.
So, how is this a lever? Where?
It's like this.
What's at the center of a lever? What do you call the thing that, well, not the center? What's the lever pivot around?
It's like a twisty thing. I don't know what
a
it's
joint?
A fulcrum?
Cartilage?
Yes.
Yeah, so in this case, got like kind of two levers going with the fulcrum way here at the very front, right? So there's a lever here that allows you to lift your foot. Now, the way muscles work is they work in pairs. You'll have one muscle here that pulls and another muscle. Muscles can only pull. They can't really push. So when you're pushing, yeah, but your muscles really only contract. They don't have a way to like expand and push. They really only contract. So what happens is, like, if you're trying to say maybe stretch your foot out and push something away, what you're actually doing is contracting muscles that cause those parts of your body to stretch further. You're not actually like making a muscle itself push. Okay, so most are levers. Look at that. That is awesome engineering. Check it out. Now,
The heel looks so goofy.
is this a right or a left leg?
That is
Oh, right, right.
left leg.
The right leg. So it's gonna go here. So we'll reattach here. So the way this works is these are kind of barely attached. You can take them in and out easily, but the purpose is because a human hip, it doesn't just go like this, right? You can make it go back. You can also make your hips come out to the side, can't you?
Not that
Some people
much.
can do it really well.
Wait, hold on.
Over split.
This is the non-vial. Okay, right?
I can't do split.
Some
go
people,
higher, go
yeah, and look,
Over
Over split.
over splits,
My mom had a friend that can do that.
right?
It's so scary.
So all of that's possible because the joint you have here isn't just a lever. The joint you have here is a ball and socket.
Miss Daddy, can I come up there and like measure my height to it? 'Cause I think we might be the same.
Well, after class we can. So,
Let me do the same height as Miss Danny.
and again, here's this one. Here's the left leg, right? So now here's something. There's something here.
It's different.
No, it's the same thing.
Kinda
What's
short.
this?
That's a different type of joint.
Kneecap.
It's a kneecap. It's a patella.
My kneecap.
Anybody ever seen a baby's patella?
No, I've never
They're
seen.
non-existent.
You don't really have them, do they? It's something that calcifies later, right? So there are bones in your body that you're born with that aren't even bone when you're born. They become bone over time. And interestingly, come on, look in there.
Why do I have such long fingers?
Yours are actually pretty long. You just can't see
My
them because
fingers
they're
like really
wrapped
sharp.
up inside your hand.
My skin.
Okay, you stick your foot up here. There they go. So your skull, for example, and I know it's kind of hard to see on him because I can't make him bend his neck too much. But you see, when I turn him, you see these little ziggy zaggies here? You know what those are called? They're not in there. It's called sutures, right? Yeah. But here's the cool thing about them. When you're a baby, they're not closed. They're wide open. As you grow, they grow together and they look like they've been
Don't
stitched.
you have like 30 bones in your
There's,
board?
yeah, it's a whole
But
bunch.
when you become a
They-
adult, there's
They
only,
join
like,
together.
Yeah. 205.
So think for a minute about this. Why in the world would human babies, whose brain is so important, right? Our brains are very important. Why would a human baby be born with a skull that is in pieces and not fused together? What in the world could be the reason for that?
So if they hit their head, it's harder to break it.
Well, but then your brain's right there.
Well, it
And then
needs
you
time
die.
to develop.
Gives it, yeah, a couple things. So for one thing, think about the proportions of a human baby and then the proportions of, say, a kitten. Okay? If you look at a human baby compared to a kitten, a human baby's head is much bigger in proportion to its body than is with the kitten. A kitten's just like small cat, like all of it. But human babies, our heads are big. Why are our heads so darn big?
Because of the show Boss Baby. I'm kidding.
Good question. Good
His
answer.
skull must be
Well, why are our heads bigger than other mammals?
because like we grow into our heads, I guess.
What do we have that other mammals?
Brain.
Oh yeah, we have this whole like developed neocortex, this whole frontal cortex, all these lobes to our brain. Our brains are way bigger and much more developed. How big do you think, if you were to, like, God forbid, surgically dissect my birthday boy Ozzy over here, about how big do you, his head's about this big, right?
How old is the baby?
He's
turning?
4 years old today. About how old do you think his brain would be in there?
Maybe
I
like.
mean, how big, sorry, how big would his brain be? Here's his head.
Maybe like that.
If his head's the size of an apple, how big is his
like,
brain?
this, like the size of an orange, maybe like a cutie
It's
orange.
like a strawberry. We're tiny. But ours is much bigger, right? Our heads are much bigger because our brains are much bigger. Okay, so now wait, we need to take this step. One more thought here. Take the thought one more step. Man, my brain's not on. So we're born with such giant brains, so we have big heads. Okay. Why then is our skull in pieces?
I don't know.
So
Brain's too big for the head.
it's not about the brain being too big for the head. It's about the head being too big for the mom. So when babies are born, human babies are born, their little heads brain spaces and all get squashed.
They look really freaky. They look
Yes,
like
that's why they're born with little pointy heads, and then over time they round back out. Yeah, what happened? Yep. So yeah, so we have different joints. So, and we have, this is a joint too, even though it's considered like fixed and immovable. So what do we call the tissues that connect bones to muscles? Oh, Lewis. There you go. Tendons connect bones to muscles. And what near the tendon acts to attach the bone to the fulcrum of a lever? Do we know? All right, Carlos.
Joints.
There you go. There you go. All right. Muscles can only, what did I say? They can only pull, right? Okay. They don't push. So even if you're pushing something, your muscles are not pushing. Your muscles are still pulling, even though that sounds counterintuitive. That's what they're doing. All right. So tendons connect muscles to bones at the joint, right? And this is how you get your lever action. What do you call the points where you connect joints to joints? Not muscles to joints, or not muscles to bone, but bone to bone in a joint. What do you call those tissues? Do you know?
Like a soft.
That's a good question. So a ligament. So tendons connect your bones to your muscles, and ligaments connect your bones to your bones. So you've got ligaments all in here, and your knees, and in your hips, everywhere. Ligaments all over, right? Interesting tidbit. Tendons, if you damage one or rupture one or break one,
painful.
what happens over time? Do you know? Like, does it get better? What happens?
Become worse.
It can for a while, yeah, but it will heal. Tendons will heal. Ligaments, if you break a ligament,
Like surgery.
My dad is an
Mhm.
ACL ligament.
yep,
Yeah, he
Flew that.
yep,
On both knees.
and two, yep, yep. So yeah, so the ligaments don't regenerate. They can't heal. So if you break a ligament, it's gone.
Why?
So the only way that your body can compensate is, yeah, the muscles on the other sides of it and around it kind of strengthen up to hold it in place. With the ACL, like you're talking, sometimes what they do is they'll take a ligament from a cadaver, which is a donated human body, and they'll put that in as a replacement. Or if ACL is down here, does your dad have a big scar on the front of his knee?
Yeah.
Okay, so
On
we
the
have,
outside.
it's called a patellar tendon graft. So there's the tendon that goes from this patella, right, your kneecap, and it goes from here to here, the muscle that connects it to this bone. And they go in and they take a piece of that tendon and then they put it where the ligament was so that you have some strength. That's what.
My friend's mom has a bone graft from a few dead cadavers.
Yep.
Not
So your joints even look like components you might find in a hardware store, like we were just saying. It's no wonder orthopedic surgeons use tools like saws and screws and hammers when they replace worn out joints. So you said your dad has screws, Nico?
Yes.
Yep. Anybody else have a screw or a pin or anything? I don't have any of those, but yeah. But yep, that's what we do. We put in screws. Yeah. Anybody ever watched a video of like a orthopedic surgery on YouTube or anything? You ever watched it? What'd you watch?
I actually watched a TV show called My Feet Are Killing Me.
Okay.
I've seen that.
Take the whole wrist joint out, and they had to
Oh,
replace it with a metal.
like an ankle replacement?
Yeah.
Yeah, I have a friend who did that recently. Yeah, I didn't even know you could replace ankles until I heard about her doing it.
I
Yeah.
had like normal toes on one side and then like skin grown over the other side.
Yeah. So if you ever watch any of those surgeries, you'll find these dudes, like orthopedic surgeons are a different breed because they legit have power tools. Look, they'll come in and they'll just cut through stuff. They'll just saw through bones. They'll use giant hammers. It's kind of brutal. Like if you watch hip replacement surgery, they actually hang they attach your feet to an apparatus so that your body hangs, at least the lower half of your body hangs. Yeah. And then they use gravity pulling on the rest of your body. It's wild. Yeah. Uh-huh. It's a weird, it looks almost freaky, but well, it does look freaky.
The joke shop too.
Yeah, the joke shop teeth. There you go. This is about all kinds of, if I can make it go, it doesn't want to go this morning. There you go. This is about different simple machines in your body. There are a lot.
I thought one was.
Simple machines in the body. And yes, I'm doing animation. Before we can talk about simple machines in the body, let's look at what a simple machine even is. According to the internet, a simple machine is a mechanical device that changes the direction or magnitude of a force. Simple machines include levers, pulleys, wheel and axles, screws, wedges, and inclined planes. Okay, let's start with pulleys. A pulley is a simple machine that consists of a grooved wheel with a rope or cable wrapped around it. So there's one example for this, and it is the knee. See, the quadriceps femoris extends down the leg and connects to our feet and lower limbs. Next is screws, which is an inclined plane wrapped around the spine. You might think there couldn't possibly be screws in the body, but you'd be wrong. Apparently, there's a bone at the top of the spinal column called the axle bone that acts as a screw. Wheel and axle is next. I can think of the different. Anyways, the wheel and axle are basically two cylinders that rotate on a common axis for different weights. The rotator cuff at the top of your arm is a wheel and axle and allows your arm to rotate around. Second to last, we now have wedges. Wedges are two inclined planes moving together. A good outside example is an axe. In the body, we have teeth and nails. And finally, levers. Levers are used to lift heavy weights with least amount of effort. Three good examples for this are T-cells, pliers, and scissors. Levels are the most prevalent simple machine in the body. To use an example from the book, the muscles and joints in your neck, the ball of your foot and your calf muscle, and your elbow and bicep are all levers. In all those examples, the bone is the fulcrum and the muscles are the input force. So that's about it. Was that 3 minutes? Hopefully it was, because this is the end.
So he mentioned a wedge. What's the wedge he mentioned?
A teeth.
Teeth. I'm going to show you another wedge too, real quick. Okay, your sacrum.
What?
Your sacrum. Okay, this is your sacrum. And again, before you're completely mature,
Oh, I broke
it's
my
a series of smaller bones, and this is your coccyx, right? That's your tailbone. In other primates, it's actually extended, right? So, do you see how it's kind of shaped like a triangle? You see it?
It's sort of shaped like
Kind of like the wedge,
the massive head.
right? You can you see the wedge shape here? Okay, so over time, the weight of your body drives this wedge down into your hips and pulls at your hips like this, spreads them. You ever heard people who have sacroiliac pain?
Never. It
Ah,
sounds painful.
This area here is your sacrum, and this is your sacrum, and this is your iliac joint. So sacroiliac pain is pain like right here, and that's where it comes from all your weight wedging down right there and squashing them. Such fun. Getting old is fun. So actin and myosin in your myofibrils of your muscles act like a ratchet. So what's a ratchet do? A ratchet is one of these things with teeth. Yep. It's got teeth and gears, and you like run something through it and it locks. So basically you're advancing something through a ratchet, like a rope, for example. You can advance a rope through a ratchet and it keeps going. It never goes back when you turn the other way because it locks. Like if you ever use a socket wrench, you turn and it tightens, but when you go this way, it doesn't loosen because it's locked. When you come back, this is exactly how your muscle fibers work. It's exactly like a ratchet. Actually, I'm going to play this one in a minute. Let me skip it for right now because I'm watching time. But this talks about how it works. It's pretty cool. I did. Go. Next one. Is there another one? Yep. Go. Why are you doing this? Next slide. Next slide. Nope. Stop. Ugh. It does not want to play. Yo, it's gonna fight with me. Look at this.
Punch it.
I'm watching the time and I don't want us to run out. Yeah, just want us to do this last couple slides. All right, so again, throughout the wedges,
That was me. When
some of your teeth are shaped like wedges, your incisors in particular, your front teeth, right? And these are wedges, and we'll do, actually you can do wedges. Let's say, we've got 2 minutes. Hold on. Let's do one of these in 2 minutes. Okay, I'll send the videos home, of course. You can watch those later. So how much work is done by a force of 50 newtons moving an object through a distance of 10 meters in the direction of the force? So work is force times distance.
Which is 500.
500 what? What's our unit?
A joule.
Joules, work. It's a lot of hard work for joules. So you would do force is 50 newtons, distance is 10 meters, 500 joules. Let's do one more. Whoops, I gave you the first clue. So if 20 joules of work are done when 2 newtons of force are applied to an object, how far did it move? So this time we know newtons and joules, but not distance. Do you know, Yusuf?
It's work divided by newtons, which is equal to distance, which is 10 this 10
Yep, what's our unit? You're right, what's the unit? Say it, Emma. Meters. 10 meters in the direction of the force, of course. And then we'll do the last one. If an object moves 5 meters with 35 joules of work, how much force was applied?
It's
What do you think, Emma? 7 what? 7 what, Emma?
cool.
Not joules. We're asking how much force. Newtons. You got it. Excellent. All right. So these 2 videos will be in your notes, so you can always go back and watch them. And otherwise, we're good and we're ready for lab already. Boom, that was fast.
Why? Oh, you're getting. I don't know what else.